Okay, we are now recording. Let me share the screen. Okay, so as I said, today we are going to discuss the perceptron, wrap it up, and then start with linear regression. I also, if you're watching the video, remember we have exam on, what's the date? The date would be April 5th, correct? Your exam is April 5th, so don't forget about that. Pretty similar to exam 1, it'll be a comprehensive exam. Okay, so you can see here, these are the modules that we have covered. And then basically, we did neural nets intro. And then now this one is just a perceptron. Let me modify the name of this to just be, so it's more intuitive, just the perceptron. So I will post here the code that we discussed last week, and you have basically the video. Okay, so there we are. All right, so that's the perceptron. That's, I'll post the link to the code here. I'll post the code on GitHub itself. We've already talked about backprop. Let me modify this one as well. So today, actually, we are going to talk about linear regression, which is the next topic in the sequence, and something that you should be familiar with already from your statistics class. All right, but it should be pretty fun. Now, all these topics are related. I like this sequence of, neural network intro, then the perceptron, linear regression. Somewhere in between, it'll be logistic regression, then neural nets, and then deep learning with. For that, we are definitely going to make the jump to Keras and TensorFlow just because it's more efficient. Even though I hear that there's a new thing called JAX, and it's a new, apparently, deep learning library for Numpy. That's what I've heard. I haven't actually looked into it, but it sounds pretty interesting, actually. I love Numpy, so certainly it's a great idea, and it's very timely, but I haven't looked at it yet. Hopefully you guys, if you continue in this field, you'll get a lot of benefit from that. All right, so anyway, so the perceptron is the topic in question. So let's go ahead back to the Jupyter notebook somewhere on here. And let's open up. So you should be seeing my Jupyter notebook. You can see it here. Now, I'm not going to repeat all of this again because this is in the previous video. So just look at the previous video. But the error was basically, see the, excuse me, the metric is now 100% accuracy. So I had, what I had done is and I don't know if I left the comment. Yeah, you can see here, I had done this, right? You can see I had done that line of code there. I had initially thought that it was going to be -1 and +1 for the classes. But the way the code is written would not work out like that. And so the classes actually end up being 1 and 0. So you can see here in this line of code, this actually doesn't do anything to the code because it was already 1s and 0s, but it just kind of emphasizes the point, right? So in this case, 1 if I equal greater than 0, else 0. So the values need to be 1 and 0, okay, for the perceptron to work. And that was it. That was actually the mistake. And so once that was corrected, you can see here, I'm going to just clear. All right. And I'm going to run it. All right. And there you can see the performance is once again 100%. So this is obviously a toy data set. It's very easy. I also, if you notice, I also printed out the predicted versus the actual, and you can see that it's an exact match for the labels, right? So if the label is 0, it's a 0. If If it's a 1, it's a 1, and so on. Does this make sense, guys? This classification?
Yeah.
Did the algorithm make sense? It's important that you understand the perceptron algorithm really well because, you know, just because all the other ones lead up into this, okay? So any questions before we move on to linear regression? No? All right, sounds like there's no questions, so that's great. I will post the code after class because I'm also going to do linear regression, and so we'll probably hopefully finish it, and then that'll, you know, I'll load both pieces of code on GitHub and then put the links on Brightspace. Now, before we start linear regression, I kind of want to go over this code again because I want you to see that there's an actual really big difference. Or sorry, no, there's actually a lot of similarities is what I meant. There's a lot of similarities between the way that we did the perceptron, and how everything just adds a little piece to it, a little piece to it, a little piece to it. But they're all building on the same idea. It's actually incredible. It's like really fascinating how, you know, something as powerful as deep learning, right, that, you know, comes down to something as simple as this. All right, so again, you know, the libraries are there. We have two functions for the perceptron, the fit function and the predict, basically. Along with that, we have a few utility functions like the activation function, and we have which is a step function, basically. And we have, which predicts 1 and 0, right? 1 and 0 value for y, let's say, given x. And then here we have the predict function, the accuracy, of course. Now today we're going to look at linear regression, so I want to emphasize that for linear regression, we will not be able to use accuracy. Okay, we will not be able to use accuracy, this formula, because this formula only works for classification problems. So when we have a class 0 and then we predict it 0, or when we have a class 0 and we predict it 1, right? So it only works for that. But in linear regression, you know, what are we predicting? We're going to predict, instead of discrete numbers are number, you guys take discrete mathematics, so you know perfectly well what that is. So discrete numbers is like, you know, zeros and ones, right? So, you know, kind of like that. Whereas 1, 2, 3. But in linear regression, you predict continuous values. What is a continuous value? You predict, you know, a person, you know, how much do they weigh? So 100 and, you know, 90 pounds, 90.5 pounds, or, you know, what is the, you know, the price of a house? So the house is, you know, continuous, you know, some continuous value, right? So 0.50, 0.7773, 1.73, you know, 2.34. So they're all continuous numbers. So it's a different kind of analysis there. Then, of course, as we did this, you know, we created the data set. You'll see that we're going to basically do the exact same thing for linear regression, create some data sets, split them and everything, all that. Then we can print the results. Then once we have our data, our X-train and X-test and all that, we fit the data and then we predict. And then we just printed out the accuracy here. Now, all of this will be pretty much the same. If we go to the fit function, which is or the predict function, which is actually one of the simplest, you know, you give it X-test, the weights and the bias. Remember NP dot, I already described what that is. A linear algebra operation, the dot product. I gave you in the previous video or lecture. We looked at the formula basically, and you can think of it as, you know, some formula that you apply efficiently in Numpy. Okay, so you want to be fast, so you use this. So basically, you perform the dot product between these values, and this is equivalent to creating the function that looks like this, right? So you hopefully remember this. Y equals W times X. x plus b. And today we're going to see a little bit of intuition of this formula even more. I mean, you probably remember this formula. You must have seen it in elementary school and high school, right? This is just the formula for a line. All right, and so we're going to take a look at it a little bit more today because linear regression, it's all about lines, basically. And then the key thing is, though, this is linear, and then usually in neural nets, then you take the linear value, the logic, basically, it's called the C value or the logic, and you pass it through what is called an activation function. In our case, we used our activation function was just this one, which is called a stepper function. And basically, if you take a look at this function, if we go to the whiteboard, you should be seeing the whiteboard now. Let me grab my lucky pen here. And so here, that formula or that function basically said something like this. We have that, and this is x, and this is, y. And what did it say? For all values that are less than 0, right? The value should be 0, right? For y. And then for all values that are greater than, what was it, 0, right? If greater than 0, then all values should be, if this was 1 and 2, 1. Right? So really, it looks like that intuitively. So let's go back a little bit. So now we can go back, just to confirm, go back to the code. That's what's so great about code. And we look, if x is greater than or equal to 0, then it's 1. If x was less than 0, then 0, 1 or 0, right? So 1 or 0. So we go back, 1 or 0, there it is. It's 1 for everything else above. So if x is greater than or equal to 0, right, it's in that direction. Otherwise, in that direction. And so therefore, this is the function that we are using, and this is called the stepper function. Now we're going to see a lot of functions in deep neural networks. This is just one of many. We're going to see the sigmoid, tangent, ReLU, and so on, ... right? The important ones for deep neural networks are ReLU, sometimes sigmoid. There's something else called a softmax. All of these are going to be activation functions, and that's why it's so nice, right, to start with the perceptron, because it lays out a lot of the background that you're going to need. But this is the stepper function, and it's going to become a recurrent theme in what we're going to be doing in neural networks, basically, as we started with our perceptron. Does this make sense, guys? It's called a stepper because, right? People can step that. Those are terrible comparisons. But anyway, it's it's like a step, right? So step function. Is this clear, guys?
Yeah, I think this is clear.
Pretty clear. All right, good. So now I'm back to the code. I'm getting back to the code here. And again, all I'm doing is I'm starting with the perceptron again. I'll probably do this every time, right? I'll start with the previous code, and I'll just kind of lay out a lot of things, because I want you to see the similarities between perceptron, linear regression, logistic. Believe it or not, when I was learning this, I learned perceptron, linear regression, logistic regression, and I would just learn these things like, here's a thing, and I never really saw the connection, so I thought all these things were, different, and it wasn't until I really had the insight that they were the same or similar that I really started to think, wow, that's amazing. And also it makes it simpler to understand, right? Because you can always start with one, and then it's always easier just to add now a little piece here and there. All right, so that is the activation function, and then that just leaves, usually the hardest part is this one. Notice here I said for classes, for 2 classes only, this was the problem last week where I got things mixed up, and it should be just 0 and 1. All right, that's actually what created the problem. So now if we take a look at the data here, we can see once again, to fit, we need X train and Y train, right? So the X data and the label, so we can find the correlation. We need a learning rate. Remember that the learning rate is the step that you take. You'll see that today a little bit more again. Hopefully, I'll do an example playing around with this learning rate so that you can actually get some intuition of how important it is, okay? Then I take the X data and I'm gonna take the shapes, so number of samples, number of features. Then I'm gonna create the weights here. Now you could create random data, right? So random data with a normal distribution of 0 and a standard deviation and so on. For more complicated problems, that is probably the recommended approach. For this one, it's so simple that we can just start with zeros, but that's pretty easy in NumPy. I think it's something like NP random float or something like that, and then or random normal, I think is what it's called. So you can play, look up those functions if you'd like, just to try out instead of all zeros, that this is actually kind of close to 0, but just more of a normal distribution. So they're different values. Now this, of course, remember, our goal is, once again, to build for the perceptron this function, right? So if you remember, we are always trying to build this function. It's amazing. And so that's the function that we're trying to build. And so we need the W, we need the bias, and then the X is provided, right? So we're going to see a lot more. Linear regression is really a perfect medium to get this insight, okay, of this equation. But this equation applies to all of neural nets, and as it turns out, it's a linear function, okay? But then the activation function is what makes it nonlinear, which is what gives neural networks their nonlinearity powers, if you will. Gives it its superpowers, right? So anyway, so we have here then, we initialize the weights and the bias. Those are initialized. Then again, I already explained this. This is actually not necessary, but it's just to enforce that the classes should be 1 and 0, which they are, because we initialized them that way over here when we did this, okay? So that actually took care of that, no problem. All right, so now we go into finally the fit function. All it does is it calculates the W and the bias, right? And those are the 2 values that we're returning here. Remember, these are vectors, but it's the same intuition. So really what this means is that this is W1, X1 plus W2 times X2 plus dot bias. Okay, that's what we're doing. So that's why we perform, we get a vector. We get all the W's and all the X's, and that's how it works. The B corresponds to whatever we're predicting here. So in this case, we're just predicting one value, therefore there's only one bias. And that obviously is reflected in the fact that the bias is initialized to a 0. So it's just one value, not a vector of n features, right? So of n values. So there's only one. All right, so now that takes us to this part here. Amazingly, this is very common, right? So the first thing is, I've explained this to you guys. It actually took me a long time to understand this for loop, okay? I understood this one easily, but it always took me a long time. Why do we do 2 for loops? Why? And I kept thinking, intuitively, I said, well, I'm just repeating, I'm just training the model on the same data multiple times. It's like I have a bucket of tennis balls and I look at all of them, and that's one iteration. Put them all back, look at all of them again, that's a second iteration. I keep doing that, and I kept saying, well, why am I looking at the same bucket of tennis balls multiple times. As it turned, I thought it was cheating, actually. For whatever reason, I thought in my mind, that's somehow cheating. But it isn't. It's actually, it turns out experimentally that it has been proven that that's the way to go. That's actually the effective way to do this. All right, so that, it took me a while to understand that, but just do it. Just do it. It actually, it makes the models more stable. It makes it better for sure. Deep neural networks are great. The only disadvantage is honestly, is that it takes them too long to train. I was reading a paper the other day about a deep neural network for Q-learning, the one that was published in Nature. I think I mentioned it before, that DeepMind and OpenAI, which are the top AI, or they're top AI organizations in the world. One I think was the one founded by Elon Musk. The other one's Google's, and they used a deep neural network to train an agent, right, like an AI agent, to play 49 Atari games. It took them, they ran it on a computer, a GPU computer with like 8 GPUs or something. It's a really powerful computer. The top of the line GPUs as well. And the computer started training, and it trained without stopping for 38 days straight. Think about that. 38 days. So that's a month and a week, or a little bit more than that. And it just trained without stopping until finally, and for the first couple of weeks or something, the model was just, it wasn't even learning, right? So deep neural nets take a long time, okay, to train. But anyway, that's a side note. All right, so finally, once you do these batches here, then the next step is to do this part, right? And this is basically, you can think of it as gradient descent, okay? So if we want to give this a name, we can call this one gradient descent. And what is gradient descent? Gradient descent is an algorithm that intuitively searches for the appropriate values and updates them, right? So you can think of it as the following. So gradient descent is this idea. So I'm going to move on to another. So if we want to think of the algorithm, we're just going to think of the intuition since we're looking at the algorithm, right? So gradient descent. Now, usually gradient descent is associated with the derivative, right? So there's a derivative. There's something in calculus called a chain rule. We're not going to get into that. If you have an interest in that, just get a there's some nice books out there called Calculus for Machine Learning. You don't really need to know all of calculus for machine learning. You just need a little bit of intuition of the derivatives, something you can pick up easily. But the idea is you have some function that looks like that, although some functions may look like this. And those are more problematic because the optimal is here, but you could end up trapped in there. Very much like a mountain range. You just never get out of there. So the optimal solution, which is W's, you might find WI, which correlates to that, but you never find WJ, which correlates to the optimal. When you have a function that looks like this, what is called a quadratic function, you're guaranteed to find an optimal because it doesn't have all these values, right? It only, this one has 4 values, this only has the 1. So in gradient descent, what you do is you're somewhere in the function, right? You calculate what is called a derivative of the function at that point, right? At that point, and then that derivative, what it does is it returns a sign like that, or 0, right? And so those 3 values, which intuitively what it means is, if you want to think of it, of the intuition of these tangents, is that basically it's a straight line touching the curve, right? This curve is touching it, and then, but in such a way that it tells you how it's sloping, in what direction it is sloping, right? Is it sloping in that direction or in that direction? And what that in that kind of translates into this idea of the sign, because if you want to go in this direction, what do? Well, W is this one. But if you go in that direction, you're going to be like that. So if this is an axis from 0 to some value, right, the W is incrementing, right? So it's plus a delta W, if you will, right? Now, on the other hand, if you're on this side, what's happening here? It corresponds to a W, let's call it W2, whatever. And the minus tells you that you're going to subtract a little piece. So it's going to be minus delta W. Delta W is just that little difference, that little piece, okay? And that little piece just tells you, and so you keep doing that intuitively, intuitively, until finally you arrive at this one. That one correlates to a 0, if you will, so it doesn't move up or down, or it'll oscillate in that little piece, but you end up basically in an optimal solution. Remember that the cost function is really the one that determines this, because this is a cost and this is the parameter in question, such as the W that you're trying to update. Okay? Now this applies to multiple features or just one, but here, this is really just the intuition. Now, this is usually handled by libraries like TensorFlow or PyTorch. However, today we're going to take a look at it just from the point of view of intuition, just to kind of get a better feel for it. All right, and so we've talked a little bit about the perceptron here, so let's go back to the code. And you can see here then we have, so we're going to iterate. We need to train, so we're going to take the X train data, we enumerate, and we grab the index, which allows us to grab the corresponding Y later, and we have the data itself. Then we simply, to train, we remember that initially the weights are zeros and the bias is 0. So they're kind of initialized randomly or just to nothing. We perform the dot product. Once again, remember, this is what? Our very famous W times X plus B, right? And so that one over here is what we're performing. We do this calculation, then we run it through the activation function. Which activation function? Our stepper function, right? So we go through our stepper function over here, this one, right? And it just gives us this nice intuition. So now we go back, we have a Y-pred, right? We have a Y-pred. So now comes, we compare the predicted with the real value, right? Because we want to see, okay, how well does our model predict? Well, we got the model, we've got the real value, let's compare them. How do we do that? We take Y-pred and the difference between that and this one. And what is this one? This is the actual data with the index, right? So Y underscore is this one, and Y underscore is really just a product of Y train. Remember, as I said, this basically changes our data to nothing. Basically, it keeps the data as is. It makes no change. But I'm just here reinforcing the fact that the label should be 1 and 0. And then once we take that difference, we multiply it times the learning rate. And this is in a very simplified way, is the same intuition as I gave you over here, that you're kind of in this and you need to decide, do I go in this direction or do I go in that direction? Where am I on the line, right? So and so do I do that, or am I on this side and do I do that? Okay, so that's basically what's happening, and you will see that for a lot of the algorithms, this is very similar. Only this becomes a little bit more complicated as we progress. Now, we take whatever this difference is and we multiply it times something. What is that something? That something is the learning rate, which we initialized over here to 0.01. Okay? So what does that mean? Once again, when we go back to this one, it kind of indicates the kind of step that we're going to take. okay? So for instance, if the step is, it's a very tiny 0.00001, what that means is that the step that we take would be very, very tiny. And if it's incredibly tiny, it would take us forever to get to here, right? On the other hand, if I just did 0.1, then that's a much bigger step. So that might be something like that. But it could be as big as something where, you know, just jumps like this. And then, you know, think about it. And it just, you know, huge jumps, right? So either one is indicated by the step size. And it actually has a very strong influence on the algorithm itself. So it's a very important parameter. So we multiply times the learning rate. That gives us how to up. So first of all, we need the value to update to, right? So now once we have that update value, then if you notice, we go here. And here then we kind of just do the update. So we look at the weights, the original one, we take whatever the values are. So initially they're 0, but eventually they're going to be other values. And we add to it a little piece. So this is going to be either negative or positive, right? Depending on whether you had an error or not. All right. And so that will indicate if you should decrease or increment the weights. So what you do is you take the update, which is this one, and then you just multiply times the corresponding x. Okay. And that will give you a way, you know, you have the two vectors, right? So you have your initial weights vector plus now your x vector times the update. You do this, and then you make, you update the values. You also do the same for the bias. Notice the bias plus update. This works because this is a very simplified algorithm. This is a 2-class algorithm, and it's only the perceptron. And that's it. This is the step in gradient descent where you update the weights and the bias. So what happens next iteration? In the next iteration, the weights and the biases have been changed. They are now different. You know, they're no longer the zeros, they're other values. So hopefully your prediction will be a little bit better. Again, you evaluate, you update, do it again. Weights and bias are different, hopefully a little bit better, and so on. You keep repeating that. Eventually, the weights and the bias will be just right. And then your model, once you run it, as you guys saw, gets perfect accuracy. Does this make sense, guys? Any questions on the perceptron?
No questions.
No questions, right? All right, perfect, perfect. So that is the perceptron algorithm. That wraps up that one that I wanted to conclude. Now, the next one that we are going to do is the linear regression. Okay, so now we're going to start a new algorithm called linear regression. So let me go ahead and save this one. And then now I'm going to start a new. Okay, so that's my new one. This, you know, I'm just going to, so you should be seeing it. I'm just going to call this one linear regression. Believe it or not, this is taking us in the direction of neural nets. All right, so now I saved it here. And actually, I'm going to rename it. This is going to be linear regression. Rename. Okay. And let me actually close the perceptron so I don't get confused. Okay, so now let's go back to the Jupyter. Okay, and that's, there's linear regression, right? So this is the perceptron here. Not sure why it says it's still running. Okay, but this is our perceptrons, and now linear regression, and there we are. All right, so we're about, let me just get a cup of coffee. Okay, so we're back. All right, so let's start linear regression now. So I'm going to click on here. All right, so let's start the algorithm. Let's start with the basics, okay? So let's start with the data that we're going to use. Actually, I'm going to open the Perceptron 2 because I just want to copy some of this. I don't really want to. So I'm going to copy all these libraries. Control copy. All right. And I'm just going to add my libraries in there. So we're going to use the same Numpy. We're going to use train test split and data set so I can get some data going. All right. So I'm also going to, if I look at it, I'm going to use this for data, right? So I'm going to create some data here. I'm going to take this one. I can actually print out my data nicely. Okay. So, oops. All right. Okay. So I'm going to do that. All right. Now, the data that I'm going to create is linear. All right. So that means that I have to change. I'm going to go to XY, but instead of make blobs, right? Notice what I'm doing. You guys can see this, correct? You can see what I'm doing.
Yeah, we can.
Okay. All right. So all right. So let's see. Okay. Sorry about that. So let's now instead of make blobs, we're going to do make. This looks kind of strange. Hold on, guys. Something. All right, so as I was saying, I think I pressed some button. All right, so here, instead of make blobs, as I was saying, we're just going to do this make regression. So I'm going to say make regression, and like that. All right, so make. So I'm going to. So I import also. Something just happened in my code here. From sklearn model selection. Oh yeah, like this. Import train test split from sklearn, import data sets. That's correct. Now I want to create X and Y, so I'm going to do data sets, make regression. Okay. The number of samples will be equal to 100 or 150, doesn't matter. Let's just go with 100. Number of features, just to keep it simple, we're going to have one feature so that we can visualize this a little bit better. Then we're going to say, because this is linear regression, it takes a different set of parameters. So here, n samples 100, n features equal 1, and noise will be equal to 20. Okay, and then random state, let's just change it to, let's say, 4, whatever, it doesn't matter. All right, and then now we have our data, right? This data is going to be X and Y data. So what that means is there's only one feature on the X axis and there's only one predicted value on the Y axis. So it's basically a 2D plane, and it makes it easy to visualize. Then I want to do the X train, X test, Y train, Y test, train test split of X and Y. Test size, we can leave it at 0.2, and random state can be, whatever we want. Okay. Now, if we want to just view the data, let's take a look at just viewing the data. So here we have print X from 0 to 10, all columns, and print Y from 0 to 10. So this should be able to run. So let's take a look. So let me save this one. Let me actually also close. I can't close that. This thing always gets in the way. I can't really. Okay. Let me do something else. All right. So hopefully that fixes the problem. All right, so now let's run this. Oh. Okay, that's when I did that. Okay. Run it again. All right, and you can see there's the data, right? So this is the X data. You can see it is 10 values on the X axis, 10 points in an X and Y plane, and these are the Y values, right? These are the Y values right there. So let's actually now also try to view it. All right, so if we view this, I think we need Matplotlib, which I believe I installed. So let's see, this would be import matplot dot pyplot as PLT. So let me run this, see if that works. All right, it ran, so the library is there. That's a good thing. So now we can go ahead and try to visualize this. So let's do here, we're going to create a figure. So we're going to say plot plt dot figure size 8,6, and then just a scatter plot, so scatter, and then we're going to print the data, right? So usually you provide for each values on X and Y in a vector, so that can be done just by taking X, the original X is fine, and then we're going to say all samples on the 0 column, and all samples in the Y vector, basically, right? So that should be enough, and then we can just provide some additional parameters like color, blue, I think. So B. Oops. All right, and then also a marker, like a 0 or something, or an O. So let's do that, O. And then the size will be some, value 30. All right, we could make it bigger or smaller. So that should be enough to set the parameters. And then let's just do plt.show. And now we want to look at our data. So it makes sense in linear regression to see if we can't look at the data. save this. I'm gonna run it. And it gave me. Yeah. So today it's like there's a gremlin on this thing. It's really odd. All right. So let's clear it again. All right. So let's go ahead and run it. Okay. So it didn't work. Iterable, not iterable. Oh, I forgot. Yeah, okay, I see the error. So in here, it should be figure size. I need to specify that. It's a tuple. I didn't provide that. Okay, so hopefully now, save it. Okay, run it again. Another error. All right. Did I not do this right at the top? No, that's it. Import Matplotlib dot pyplot as PLT. And this is PLT, so.
I know you don't have a ending parentheses for the fig declaration.
I don't? Oh, okay. Oh, great. Thank you. Good catch. Good catch. And then I have a parenthesis here. All right. So hopefully that'll work. Sometimes Python gives you these strange errors that have nothing to do with. All right. So let's see. Try it one more time. Ah, there we go. Awesome. Thank you, guys. All right, so there you can see, what is this? This is the plot of the data. As you can see, you know, the data that we generated in X and Y, we have it, this is the X axis, this is the Y axis, right? Therefore, we basically created this really nice regression data. Why is it so nice? Well, we said make regression, right? So you know, it's kind of helping us out there. You can see, though, that this looks really nice. And so what is our goal? Our goal now in linear regression is to fit a line that approximates the data. Right? So I can't write on this. I don't think I can write on this. Yeah, I cannot write on it. So let's go to the whiteboard and kind of replicate that one. So if I go over here, you can see that what I'm trying to do is let's grab a pen. Right, so I have, you know, X and Y. That's why we only selected X and Y and not X1, X2, you know. And then the data in blue looks like this, right? So it's same data. It looks like that. A lot of, these are dots, right? So they mean that if I, you know, do, you know, have a X value here, it predicts a Y. So if this is 2, it's, oops, this is 2. Right, something like that, right? And we are, so what we want to do now, the goal is to fit a line. Now, what is the equation for a line? You probably remember this one, right? That's the equation for a line. What is the m by x? It basically is called a slope. You remember that? And so we have x2 times some m value, and it tells you how the line slopes. So the line like that, or does it slope like that, or does it slope a little bit down? It's like the angle, if you will, right, and so on. What is this bias? The plus b is basically an offset on the y-axis. So for instance, let's say if I draw it over here, right, and I have that. So I could have a line that begins like that with no bias, but if I add a bias, let's say b, then, you know, that's the offset. So now the line is up here, right? The line is up there. And that's really what it is, then intuitively what we're trying to do, okay? And so therefore, those are the parameters that we are trying to learn. Remember, we're trying to, oops, not that one. We're trying to learn this one and that one. Okay, so we want to fit a line that looks, so let's say that we fit that line, this line, or that line. Which one of those, if this is A, B, C, and D, which one of those 4 lines is the best fit?
Line C.
Line C, exactly. Perfect. That's what linear regression is. That's exactly what we're doing. And believe it or not, this is highly related to neural networks. Okay? And neural networks will be a little bit different in the sense that, and this is a perfect opportunity to show you that, in linear regression, when we try to fit a line, right? So we try to fit, as we saw the data over there, and the problem is we want to fit a line. In other problems, we are trying to fit a line still, but in a different kind of space. So here we have, these, dots like this in one side, and then we have dots like this in another side, right? And so the blue is class A, the orange is class B. We are still trying to fit a line, but this time around, we don't want a line that kind of fits the direction of the data. Instead, now we are trying to fit a line that separates the data perfectly. You see that? So intuitively, it's the same thing. We are trying to build the same line. Think about it. But we are trying to change the orientation of it, right? So it's like we're trying to rotate it. That's all we're trying to do, right? So we have an algorithm where we try to fit a line of some kind, but we're trying to rotate it because the problem in this is linear regression, right? Linear regression, and this is classification. We want a line that separates the samples in the data. So the objectives are different, and therefore it changes a bit of what we're going to do. We'll see this when we look at logistic regression, for instance, the next one, right? Or neural nets and deep neural nets. But in this one, linear regression actually gives us a lot of the pieces in a very intuitive way. And so we can actually, figure out pretty much understand that all we have to do is kind of rotate it a little bit to meet the objective of perfectly separating out these samples. Okay? So that's really the idea. Okay, so hopefully that makes sense. Stop me if you have any questions, but that's the intuition, right? So we want to fit that line. So we go back then to our nice algorithm over here, and we have the data. Now I want to create that red line, or whatever color that kind of fits the data. All right, so we'll do this again, but for now, let's just kind of take it out. All right. So hopefully we'll come back to it when we fit a line so that we can see that the line does in fact fit. But this just gives us a little bit more intuition. Now, keep in mind, you can't always see the data in machine learning. That's one of the big problems because the data is so high dimensional, right? We can only see in 2D and 3D, and you guys know that whenever you have 4 features or more, you're basically talking about hyperspaces or high dimensional spaces, vector spaces. All right, so we've got our libraries, we've got our data, right there. And then now we're gonna need to do the evaluation. I also said that we can't really do it with accuracy, unfortunately. So we are going to need a new metric. Linear regression does not so let's go over here. Oops. All right, so we can't use accuracy here. Why can't we use accuracy? Remember, our data is not like this. It's not, it's not class 1 minus 0 or 1 minus 1, right? So we don't have that data. Instead, what we're gonna be predicting is numbers. We're gonna predict, like you saw in the data, right? We're gonna predict, 0.35, and the real value is 0.41. Oops, should be a 0. Do you see that? So this is actually just going to give us a difference, right? So the difference between that is 0.06. Do you see that? That's what we're going to be getting. We will be getting these kinds of values like this, okay? So, oops, like that. So then let's kind of work this out, right? So this is what we are getting. So again, let's go back to our our notepad. And we can take a look at the data again. So, you know, we are getting values. So, you know, we have our data. This concept, I remember, I'll tell you this story. I remember this concept. I was confused with it for a very long time when I was in school. Very, very confused. I literally remember the day, I'll never forget, when I was in the classroom and I finally got the concept. I finally was like, oh, that's what it is. You know, it took me, it's embarrassing, but it took me the longest time to get this. Anyway, so what we're doing here is, these are the real values to blue, right? If I predict this line, right, this line, right, that's the prediction. Then how do you measure how good that line is? Well, you have to compare for that given x, right? So for, let's say xi, right? So for that given x, the real y should be that one. That's the real y. However, the predicted is that one. You see that? So what you do is you take the difference. Let's call it difference I. You see that? And I take that difference I. Then, actually, let's call it delta I, since we're going to be using deltas later, delta I. Then I have another one, x2. Oh, actually, I can use 1, right? 1, so this is 1. Then I take x2, and again, that's the dot for x2, the real, but the predicted came out here on the, still in the straight line, right? So again, you take delta 2, and then this, I'm going to make it delta 1. Do you guys see that? And you do this for every single point. So that's going to be D2, and then D3, and then dot, 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 Dn for all of them. And then what do you do with these? You sum them. And that's going to give you a value, right? If these are large, then it's going to be a large value. Now, let's look at another one. Let's say that I come up with, I'm going to use the same points, come up with that line. Do you see that, guys? I come up with this line, so that this, call it A and B. So this is A, this is B. I do the same thing. I'm going to sum, I'm going to change colors here. So sum, and I need these values. So again, for x1, right, the value is this one, the real one. The predicted is no longer that one, right? It's no longer that one. Now it is on this line. So it's going to be basically that one. You see that? Now I take the delta 1. Look at the delta 1 there. So this is delta 1 green. These are delta 1 blue. I do the same for x2. That's the real one right there. And the predicted is on the red line. I take this difference. That's delta 2. You see that? And then I repeat that for all the points until delta n. Take the sum, and I get a value. Now the question is, when you do this sum of all these values, which one of them is which one is higher? Which sum? The sum of A is higher, or the sum of B is higher?
A.
A is higher. Excellent. A is higher. So, how can you use this to say which line is better? What would be your conclusion? Imagine that you try multiple lines, because remember that having different sets of W's and different sets of B's give you an infinite number of lines, right? So I can have you know, I'm going to use another color, that line, that line, that line, you know, tons of lines, right? How do you know which one to choose? Which one do you choose based on this intuition here? Which one do you choose as the best?
Wouldn't it just be A? Because we're saying that
A
the
is the
sum of A
highest.
is
A is
great.
the highest, but so A is the highest. Now look at this line. Now I'll ask you this question. Of these, just look at this picture here, the two red lines. Which one is the better fit?
B.
B, right? B. So even though A was the highest, B is the best.
Okay.
And B is the sum of the sum of all the differences that gives you the smallest value. So you really want what?
B.
B. Why B? Not just B, but why B? Because of all the lines, this one gives you the smallest sum of errors. Do you see that?
Yeah.
Yeah. And so this is sometimes called LSE, least squared errors. It's sometimes called MSE, mean squared error. Whatever it is, or the sum of errors, whatever it is the one that minimizes this sum. That is the objective. Do you know what I mean, guys? And so you usually do a count. What? Sorry?
No, I was just going to say yes. I was responding to you.
Yeah, all right. Yeah, exactly. So that's what it is, right? So that gives you, now, because the difference, remember, and last part of this is that because the difference is going to be, could be also on this side, right? So the point could actually, I drew them all up, but intuitively the points could have, the predicted or the real ones could be, or actually I could say they're on this side, right? So they're on this side, right? So, and so they can be positive or negative. They can be positive or negative because they can be on either side. So that's why the only last thing is we're going to say the predicted y minus the real, or the predicted is hat minus the real one squared. That way we get rid of that sign. We just take the difference. And so that takes care of it, right? So we end up basically with that formula. And then we take the sum of them and then divide it by the number of samples. It kind of gives you an average. And that's what our formula will be now for our accuracy. So if we go back to here, right? So we go back here. Now we can see, okay, I need this function for accuracy. I'm going to define it as mean squared error. I'm actually just going to call it MSE. I like, you know, that. But, you know, let's define it here. So mean squared error, right? But that's the intuition I just gave you. And what do we want? We want to minimize this as much as possible. So then we can always give it y true. We can give it the you know, all the samples because we're using Numpy over here. So y true versus y pred intuitively should give us what we want. And then colon, like that. And now I'm going to just, you know, return. And I'm going to say numpy. I don't even have to do all the math. I can just use the built-in mean function in numpy. And I'm going to say, you know, what I just wrote before. So y true minus y pred, but squared. Right? So I'm going to get rid of the sign. So squaring in Python is just like that, double asterisk, and then 2. If I want a root of something, it's just like that, remember? But just like that. All right, and if you look, that's, you know, pretty much what I was writing over here on the whiteboard, right? I've captured that intuition. So I go back to my NumPy code, and you can see I've got myself what I need. And that's it. You know, that's it. You know, pretty straightforward. at this point, we are basically in good shape. Got our data, we know it works, we've got our function, MSC. This will allow us to evaluate this model over here, right? But we still need to fit the line. We need to fit the line for sure. So now that we've done this, we need to go back and define the rest of this. So now, what do we need? We need a, over here, we need some new functions. So I'm going to save this one. Okay, and now I'm going to let's go now to so just like we did in the Perceptron, let's say. So just like we did in the Perceptron. Hold on, let me think about this. So just like we did in the Perceptron, now we need to train and fit. So train and fit, and we also need a few other parameters. So let's do that actually. So I'm gonna oops, what happened? Here. All right, so I'm gonna save this one. I'm gonna say define, right? Define my predict function, predict, just like that. This is a linear function, right? We don't need an activation for this one, as it turns out, right? Because all we are, we don't need a stepper function or anything like that. We're just going to predict the value. Okay, guys? So then I'm going to say here, y pred, I like to use that term. So y pred, and then this is just going to be numpy dot, the dot product that we already discussed extensively. And what do I take x, comma, and then I take the weights, just like we did in the Perceptron, weights, and then I do plus the bias, okay? Plus the bias, and that gives me then my value. So I'm going to do return y pred. I predict, remember I'm just doing the line function that we've discussed. Obviously this function takes the x data, so this is very much the same function we have done before. We're going to pass the weights and the bias. Now, all these parameters are what we need to learn in the train step, okay? We need to learn these in the train step. So then we need to have a fit function. So now I'm going to say, so notice I'm just repeating a lot of what I did in the Perceptron. It's amazing how all of this was clearly defined in the 40s when they didn't even have like digital computers or electronics, just using more mechanical relay-based kind of things. But so define fit, our fit function, pass or something. All right, so now comes this part, right? So we need to define a few parameters. So we need to define the learning rate, okay? Remember, I already talked about the learning rate. Think of the step of the giant in the valleys. So learning rate, actually I'm just gonna say LR, stands for learning rate, don't forget that. And I'm gonna use something like 0.001. Some value, I'm picking some value. We're gonna play with that parameter. Let's get rid of the pass. Now, what else do I need? Number of iterations. Remember, I explained what this is, the thing that, you just keep looking at the bucket of tennis balls over and over and over and over. Look at all of them, then start over again, look at all of them, start over. So I think for this one, we should do maybe, let's see, 1,000 maybe. We can try, yeah, 1,000, let's say. Let's see how it goes. Okay, so let's define this one as, let's say, 1,000 iterations. Okay, now comes basically the next part of the structure. So remember that in this one, we are, the goal is to calculate the weights. So we need to initialize the weight vector. Okay, so we're going to say weights, right, just like that. Again, we could initialize this to random data, random normal distribution. 0, because these are easy problems, 0 should be enough. But I leave it as an exercise for you guys to kind of figure out how to do that. Additionally, another thing we probably want is the number of features, right? We only have one in this case, and the number number of samples. So actually, n sample should come first. Number of samples, number of features, that we can get that from x. That means that x will need to be passed here. So x and y. Oops. Let's use the convention where x is an uppercase, y is a lowercase. So n samples and features, and then we're gonna do x dot shape, which should give us what we need. It'll give us the 2 parameters. All right, we initialized our weights to n numpy.0. So now we can say, well, we can say the weights just correspond to the features. So there's only one, and there will only be one here. And features, the bias, we can just initialize that again to 0. So I'm just going to do 0 right there, and that's it. That's and then once again, our gradient descent algorithm, which is actually a lot more straightforward than one would think. So gradient descent, just add a little comment here. All right, and then now for the 2 for loops, right? So for, and I don't need anything, so I can just do this for I in range, and then n iterations, right? It's going to be 1,000, so I'm going to do 1,000 passes, it's called. And then I'm going to do the second for loop, and this one will be basically so we need to think about this one, how we're going to do it. Now, initially, when we did the perceptron, if you remember, we actually enumerated, right? Enumerated, and we would take each value and kind of look at it. This time around, we are just going to take all the data at once and do an update to all the data at once instead of doing it individually. All right, so that it can be done in both ways, but let's just take this approach. All right, so now what I need to do is I'm going to take, instead of doing xi, right? So if you remember xi something, so let's actually go back to, okay, I closed, let me do this. All right, so if I look at the original one, the perceptron, you guys can see that in the fit, you know, I would enumerate through all the individual ones. I would get for each x, I would get like that row xi, and then I would perform the operation on that xi, and then I was updating them all at once. This time around, I'm going to just do one update, okay? So I'm going to go over here and just take all the data at once. Usually you do have the two for loops in general when you do deep learning because you take data in batches. Here though, because you're talking about millions, right? So I can't, in deep learning, I can't give 2 million all at once. And so we're going to have a second for loop to read the data in batches. Here though, because the data is so tiny, I don't need that second for loop. Can you guys hear me? Just want to confirm that I'm not just talking. Okay, good. All right, so let's do that then. I'm going to, so again, there would be a second for loop if I took individually each sample from the data. Like this one has 100 samples, right? So this one is really 100 by 1. It could be 100 by 2, 100 by 4, depending on the number of features. And we could just take, with a second loop, you know, out of those 100, the first one, the second one, the third one. However, now you could do this in batches, which basically mean if I took batches of 10, I would take the first 10, then the next 10, then the next 10, and I could have a for loop like that. However, because this is so small, I'm just going to take all the data at once, so I don't need the second for loop. Okay? Now that I have this, then I can proceed to just do the same thing, right? So I'm going to create ypred, just like before, and it's going to be just like before, np dot, so my dot product function, and I'm going to do a bias here. This works, the bias works, even though it's not a vector, because of something called broadcasting in Numpy. And so now all I do is I take all the values in X. Notice that this takes all 100, right? Because here we provide all 100. So it takes all 100, and it's just going to perform a matrix multiplication with the weights vector, okay, which is just of 1. But now we're going to end, ypred is going to end up having all 100 in there. All right, so ypred is 100 by 1. Okay, and so that's just, you know, something that you can do with NumPy. And now, believe it or not, there are only 2 things that need to be done. Okay, one thing is, and let's call it compute gradients. Compute gradients. The second part is something called update the parameters using the gradients. So parameters using the gradients. That is it, okay? We have to do those 2 steps, and then our algorithm would be done. So let's start with the easy one. Update the gradients, okay? So to update the gradients, what we need to do is we need to take the weights, right? The weights here. And we're going to modify them, update them, just like we did with the Perceptron. This time around, it turns out you just use minus the learning rate, LR, which is this little parameter, right? Which is the step size as a factoring or scaling value, times something called DW. Okay? Now, what is DW? That is the gradient. So first, we need to compute for this example, what is DW? You see that? We need to figure that one out. Then we update the bias. Okay? And to update the bias, then we're going to take the bias minus LR again times DB or D bias, right? So that's the gradient for the bias. DB, like that. You see that? So this one is done, right? So this is just the update. The problem is we need to compute what this is. Okay, we need to compute what this is. This is a little bit more complex now than before. If you remember in the Perceptron, we also did something like this, right? We would take the difference between the ypred and the real, get that value, and then that value was basically used here. The sign really doesn't matter because the DW will either be positive or negative. So it doesn't really matter. And so that's it. This is what we do. All that's left is we need to compute how to calculate DB and DW. Okay, DB and DW. Now to do this, we're going to go back to the idea of that we discussed here. So if I go back, we're going to go back to this idea here. If you remember the idea of the slope. So the slope now comes in, right? The slope now comes in. Now, we also use this formula here, all right? This formula here, Okay, so let's think a little bit about that. We need to figure out what dW and dbias are. Okay, we need to know what they are. So what we need to do is, if we go back to this idea, right? So we have this idea. We go back to this idea. Now, we are going to do this for the W and for the B's, okay? So I'm just going to do it for now for the B's. They're separately. So this is W. Excuse me. And this is the cost. So we said that it should be Y minus Y hat. Y is the real data. What is Y hat? Y hat is basically WX. Y hat is WX plus B. You see that? So we calculate the parameters of W and B, right? And that gives us the line equation. Remember, we are trying to build a line, right? So it makes sense that the line is this. Then we take the difference, square them. Oops. And then sum them, right? Divide them maybe by n, 1 minus n, right? That's what we're doing. Turns out this equation looks like that, right? Remember, there are two equations. Let's call it equation 1. So there are two equations, equation 1 and equation 2. They're two separate things, okay? One gives you the line, but as it turns out, if you look, there's something in common with them, right? What is it? Y hat. Y hat is in both. Therefore, we can rewrite this equation as such. We can rewrite it as 1n sum of y minus, instead of y hat, now we're going to say wx plus b, right? Just like that, squared. You guys see that? We took both equations, the one of the line that predicts the value, the real, this is the real y, the x test, or y test, sorry, and this is the equation. You see that there? And now we have indicated, we have written that equation in terms of W and B in this case, right? So now what we're going to do is, you remember the intuition. We said that if we pick this W1, let's call it, it gives you that cost 1, let's call it. If I pick this W here, let's call it W2, it gives me cost 2. If I pick this one, W3, it gives me cost 3. Which one of these W's is the best W for the model?
W3.
W3, perfect. Perfect, because that is the lowest cost and that is the optimal solution. Remember that we said intuitively to find whether we want to increase or decrease, right? We want to know if we want to go in this direction or in that direction, depending on where we are. So we take a W and we figure out where we are in the equation. As it turns out, there is a way of knowing that called calculating at this point, at W1, at that specific point, I calculate what is called a tangent to the function at that point. And the important of this is it tells me whether I should go plus or minus, okay? Or I'm at 0, right? It's like that, and so that means I'm at the optimal. Now the question is, how do you get that, right? So that's the question. How do I do this magic of, oh yeah, calculate this tangent and you're done, right? So, well, it turns out that, and we're not going to go into this because, that would require you guys, to be fair, for you guys to have taken calculus. So the idea would be that we would take this function that I just called J, and I'm going to take the derivative of J in terms of W. Okay, do you see that? So that, you know, in calculus, there's an operation that takes a function and takes the derivative of it, and then that just means that the function is modified, right? So this equation that you see here becomes another equation. So I'm not even going to write it out, but it just becomes another equation here, right? And then I do the exact same thing with the bias, right? So then assume now I have another, instead of w's here, this is b, and the same cost function, right? And the same tangent idea and everything. How do I get those tangents? I would take j. So let's just say, you know, I'm going to do the derivative and get this value, which is easy. You know, it's something that it can be done. So we don't even have to worry about it. And what, you know, and then I would take the derivative of j in terms of the bias, and then it gives me, so it takes this equation, right? This equation, because remember it's j, right? So j represents this equation, and we take the derivatives of them, and then we get the modified function. What's so great about that modified function is that now intuitively we can think of it as it has captured this idea of the tangent. And now we know what the tangent looks like, and so we're going to get, you know, should we go plus, right, in that direction and increment, or should we go in that direction and decrease w? Okay, so without getting into how to, you know, how do you calculate the derivative and all that, I'm just going to write out these functions. So I'm only going to write out, you know, remember that when you do this, you would usually just write it out in you know, in TensorFlow, you never have to do this, right? So that's why I'm really not going into it. Now, if you had to do it, you know, that'd be a different story. But TensorFlow has been designed so you do not have to do this part, right? This is done. You define all these things, and then TensorFlow behind the scenes does all that magic. So you don't have to worry about it at all, okay? Does this make sense, guys? Does this intuition make sense? Are there any questions?
It makes sense to me.
Yeah, exactly. So then in the code, we're just going to call this dw, okay? And, you know, it's just some name, and then this one is going to be db, okay? So they're just going to be, remember, they're the derivatives of the original function, you know, which is the cost function. So we're just going to write it out in our code for this particular example. Remember, this derivative depends on everything, right? So the derivative that I'm writing only depends on this particular case. Other cases, we would have to get the derivative of them and so on. So it would be a lot of tedious work. The code today is just for intuition, but what's great about it is that when you do this in TensorFlow, you know, which is the professional way of doing our PyTorch, you don't have to do it. It's already, you define this equation, yes, but you just provide that as pretty standard, and then you just get the result. So now we can go back to our code. So that's why TensorFlow and PyTorch and all those are so popular, right? Because they take care of that. So again, you know, let's, if we go back to the, here, right? So these values, this one, dw here, and db, these two, the derivatives of the original function, can now just be written here, okay? And so in these parameters, we can just specify them for this particular case, just to see that it works. And so you can see, we're just going to take, so to compute them, we're going to say one. So this is, remember, this is the derivative result of the derivatives of n samples, right? And times, you know, a dot product, since we're doing everything like this. So np dot. And it's going to be, this parameter is still kind of there. As it turns out, all of these kind of always look a little bit the same. Y pred, right? So you can see what's important is Y pred in there. Minus y, right? So it's going to be y because it's this one. All the data, all the real data versus all the predicted data, okay? So we take the difference of them in this case, and then of course, and then we multiply that times the x, and we're going to do x dot t actually. T just means transpose, so we're just kind of like rotating the matrix so we can do this operation. As it turns out, the derivative of the original formula is, in terms of w, is this. Okay, that's what we get. But as I said, this would vary too much. You know, if we had, you know, with a lot of scenarios. So this is what it comes out to. And as I said, this is something that we don't have to do all the time, right? Because the libraries like TensorFlow, etc., PyTorch, probably JAX, if that's a real thing, will do it for us. All right, and then this one will be, the derivative should be the simplified. By the way, I should say, you know, the derivative of the math functions are always a little bit different because there's always simplifications and optimizations that you can do. So, you know, there's like real math, you know, in pen and paper, and then there's numerical methods. Numerical methods are like approximations of the math that's good enough, that's really good enough. And so you can think of it that way. So they're not exactly like, if some of you are curious and try to work out the derivatives on your own by hand, you might see that they're not exactly like this. But that's just because, remember, there's always these simplifications. So that's why there's too much that's involved in it for it to be practical. And that's why people just kind of do these things. The libraries take care of this, and you don't have to do it. But anyway, that's it. That's basically it. So if you notice, you predict the values, you compare them here, right? You compute the gradients by using the equations from the derivatives, as I explained, and then you update over here. And that's it, right? So now we're done. And so we have done predict and fit, and we are now ready, hopefully, if I did everything correctly, we are now ready to test. So hopefully it'll work. All right, so now we can go down here. You know, we can predict our line, why not? All right, and let's now train and test. So now we need to train and test. So I'm going to do weights, bias, and I'm going to say fit. I fit it with, now I need to fit it now with X train and Y train, right? X train, Y train. That gives me my weight and my bias. And then I'm going to say, what was it? Predict. Yeah, predict. And this will give me my Y pred. So then this is going to be predict, which will take X test. Right, so this should take X test, and it should take the weights and the bias, just like we did before. All right, and that gives me my Y pred. Then now I'm going to calculate my MSE from, and let's say MSE result, which is MSE, which is this equation formula over here. So it takes Y true and Y pred. So it's going to take Y test, because that's what we created over here. Y test is right there. And it takes Y pred, like that, right? And then we just print MSE. And what we want is for the MSE to be as low as possible. That, you know, however, that's going to be a little bit difficult to measure. So we're going to see. Let's just run this to make sure that it doesn't error out, because it'll probably error out. So let's see. Yeah. Okay, what's the error? Oh, typo is not defined. Weights is not defined in the for loop. So it's easy to fix. Right, this one should be weights. Try again. All right, so I'm almost done. Let's hopefully, if this works. Doesn't like it. Non-iterable type. Did I not? I think I didn't return. Okay, so it didn't return. Weights and bias, because that's the answer. All right. Try it yet again. Okay. Run. Okay, so now it printed something. Did I not? What happened to MSC? I wonder if it's oh, yeah, that's right. Sorry. I'm calling the wrong thing. It should be MSC results, not MSC. That's what I was saying. Okay. So then I save it. Do this. Run it. All right. There's our value. That's our MSC, right? Do you guys see that? That's our MSC. So I try, remember this number, 4283. Now, if I try, let's say, just like that, right? I changed the step size a little bit. 4283, now I run it. This one is 1276. It's lower. So intuitively, I can choose that the second one is possibly better. All right, it's possibly better. Okay, now we can't always, so that's how you would measure it when you have very complex data that you cannot visualize. However, there might be some situations where you can in fact visualize the data. And so, and we have a few minutes left, so hopefully if I do this right, we can plot the results. So let's do that. Let's try it, okay? So I'm gonna try to plot this really quick. So I'm gonna copy this one again, right? Copy that. And I'm gonna create in this case, I'm gonna calculate. I'm going to predict. I have wide, I have wide pred, right? I have wide pred here. So now I need to do the whole data. So I'm going to take y predicted line, let's say, yeah, pred line. And I'm going to use predict, and this time I'm going to fit the entire data because that's what I had plotted, right? If you think about it, I plotted this, right? So now all I want to do is I want to plot the line on top. So I'm going to plot the line on top. See if I can do it like this. Plot the line on top, hopefully, of all the data, which was X, comma, the predicted line Y, is not Y pred line. I know I only have a few minutes left, but I'm hoping to finish this. So Y pred line, color, black, comma, line width. This is just like parameters 2, and then label something like prediction. Pred, let's say. All right, and then show. I wonder if this will work. All right, let's try it. So I'm gonna save it. All right, I run it. Okay, didn't like it. Oh, that's just in the function, right? So wait. Bias, okay. Save it. Run it. Name weights is not defined. Misspelled. When you're doing things in a hurry, everything breaks down. All right, so once again. Ah, do you see that, guys? There we go. What do you guys see? Guys, can you hear me?
It looks like it's showing a slope.
But it's not a good fit, right? Would you say this is a good fit?
No.
No, and that's why we get a value of 4283. You see that? It didn't fit the line very well. How about we just change the learning rate, the step size? So it didn't find the optimal, right? It didn't get to it enough. Possibly if we had incremented this to 10,000, with this step size, it wouldn't. But the giant was too tiny. It was a very tiny giant. Now let's do a bigger step size, right? And do this, do that, and then run. What do you see now?
That's a much better fit.
A much better fit, right? A much better fit. Exactly. Let's try 10,000 iterations. So I'm going to do 10,000 iterations, save it, clear, and then run it again. Ha! What do you see now?
That's almost a perfect fit.
Much, much better, right? And you can see that a lot of it has to do with, playing with the parameters of the learning rate, giving it enough iterations to learn. But at the end of the day, we were able to fit a line to this, and our linear regression algorithm has worked. Does this make sense, guys?
Makes sense to me.
Any questions? All right, so we're done. That's it. So we finished linear regression and Perceptron. So that's really good. That's a lot of progress for today. So I will be posting these things on the YouTube, right? And then on Wednesday we'll be able to continue. All right, guys. So we're gonna stop here for today, and I will see you guys on Wednesday. I'm gonna stop the. I want to save this actually before. So let me just save the PDF and then save it. All right, so I got it, I think. All right, so we'll stop here for today. I'm going to stop the